I'll take some short time to introduce you to Strusoft, who we are and what we do. Today we're going to talk about our 3D finite element method software, FEM-Design. Besides that, we also produce other types of software like WinStatic for individual element calculation and design, BIM Energy for energy consumption and optimization software, Impact Precast and Reinforcement for prefabricated element production and design, especially for factories, and Prestressed for pre-stressed concrete beams and hollow core slabs. If we take a look at Strusoft's history in this timeline, stretching from 1982, when it was part of Skanska Construction, up to 2021, the present year, when the latest version of FEM-Design 20, has been released. And another milestone would be the acquisition of Buildsoft, the structural design software company in Netherlands. We have more than 10,000 users around the world using our software. And we have offices around the world with the headquarters in Sweden. Let's switch focus a little bit to FEM-Design, the program in question for today. FEM-Design is very advanced when it comes to interoperability with BIM software and other modeling, structural modeling software. It works very well with CAD drawings, which we will actually have a look at today. There's a very good BIM integration with BIM software like Autodesk Revit and ArchiCAD. There's also a very good connection with IFC files. This has been a special focus in the latest version, FEM-Design 20. A strong focus was set on IFC modeling, IFC connection. FEM-Design can do a lot. We have the 3D analysis engine and design modules, which are comprised of foundation, concrete, steel, timber, composite, and masonry in FEM-Design 20. There are some special functionalities in FEM-Design which make it a very easy to use and powerful tool, like the crack section analysis for concrete design, where the reinforcement is taken into account and stiffness of the material is decreased, along with any cracks that might appear during an iterative process. It is also possible to model the soil as a 3D finite element model and have a very realistic behavior of the soil and the superstructure as well. You can study the whole superstructure and soil together in one model. Another element that makes FEM-Design and sets it apart from other software is the continuous development. We have a very strong team of developers in Budapest, Hungary. There are several releases of new features during the year, and with one main release of a completely new version every year. As I mentioned, FEM-Design 20 is the latest one, which was released earlier this year. Furthermore, this development process is strongly connected with the users. Once a year, we actually have a meeting with key users who share experiences with the developers. It is actually you can call it a brainstorming process where the users bring their experience from using the software and suggestions and ideas of how FEM-Design could be improved in order to help them. So there's actually a direct input from the users who are involved directly into the development of the software. That was a short introduction about TrueSoft and FEM-Design. Let's focus now on the program itself, FEM-Design 20, which will be used. Maybe I'll switch between some models which are made in FEM-Design 20 and 19. I actually have some of them open here. But let's start by opening a 3D structure model. Immediately when I open the program, I am prompted with a configuration window where I can choose the Eurocode from my national annex. This is my workspace where I place my objects and elements into a 3D workspace. I can also choose to make it a 2D view from different angles if I feel the need. The top menus are divided into tabs. Starting from left to right, I have the structure, loads, finite elements, and analysis tabs. These constitute the calculation engine. The names suggest what these tabs are focused on. Of course, in the structure tab, again, moving from left to right in a flow, you start by defining your structural objects from stories and axis to bar elements, shell elements, support elements, and specific modeling tools for FEM-Design. In the left side of the screen, you have your CAD tools, which help with modeling and drawing your structure. I have very familiar CAD tools here, like move, erase, rotate, copy, array, mirror, and some trimming functions like break, chamfer, fillet. Again, familiar functions, familiar CAD functions, which make modeling easy and intuitive. We'll actually get into the modeling in a second. Here's the quick tools, where you have a quick access to your drawing layers and your object layers. You can switch the layers, the corresponding layers to your specific objects on and off, and some drawing layers, and the results pane, which is probably more interesting in a second when we actually get some results. Here in the bottom of the screen, you have actually a command prompt, which is very handy when using new tools, for example. It will actually prompt you with the next command that the program expects from you. From right now, I'm trying to draw a beam, and it says just start point. So I know I have to put my start point and end point. Maybe for drawing a beam, it's not that, it's something very intuitive, but when I get to some tools, some more advanced tools, that comes in very handy actually. Of course, here I have a monitor of my position on the workspace in coordinates X, Y, and Z, and some buttons for snapping. Okay. Let's start to place some structural elements. Let's say I want to place a column. Choose here above my cursor. I can also place it below. This is a standard menu for all of your structural objects and elements, where you can set your properties, physical alignment, analytical model, and every element has its own specific methods or tools, if you will. In the default settings, I will choose my section. I have here concrete, steel, timber, and hollow core for the sections. Material. Stiffness, where you can actually modify the stiffness with some stiffness modifier factors. This indicates where the factors actually apply in the stiffness matrix, and end conditions. Okay, so I start placing my column. I can actually type in the coordinates here in the command line, or I just click somewhere on the workspace. If I want to place my next column, a very useful tool is F12, which allows me to place the next column relative to the position of the current already placed column. So if I just enter an X of 6 meters, it'll just place it at a 6 meter distance. I can choose to copy these elements, and again, by using the F12, I can enter some coordinates relative to this point. And very fast, I'm already starting to shape my structure. Let's place some beams in a very similar way. All these default settings I can set and choose sections and materials just like my columns. I just start placing them. Again, if I'm not sure what what I'm expected to do, I can follow the command line here, which tells me what I'm expected to do. Okay, I'm just placing some beams here. A very nice and important tool is the story tool, which I will show its functionality right now. I can start defining stories. I can enter them in a table like this. I can enter them manually. I can choose generate and say 4 stories times 3 meters. And I am actually generated some stories. Using the copy story, I can copy the specific elements to a story onto my next stories. So if I choose the source as the story number 1, and then I copy to story number 2, 3, and 4, 3 stories copied, and all of my elements are adjusted and aligned to those respective stories. Afterwards, once I have these stories defined, I can actually scroll through them. This is particularly useful when I'm viewing results, when I want to view results for a specific story, like deformations or reinforcement, applied reinforcement or necessary reinforcement in a concrete slab, so forth. So I can see that I can model my structure directly in my workspace. By defining all of my structural elements, beam, columns, under I have truss members here. I have plane plates, which are surface elements. I can define profile plates, timber plates, plane walls, and timber walls. You can define CLT elements as well. We'll take a look at that a little bit later. What is also very easy to use is drawing from CAD files. So let's just open maybe a new window, a new FEM-Design model. So if I have a drawing, let's say this one, I can just drag it in my workspace. And I am prompted with all of the layers from my drawing, which I can choose to import or not. Here I can choose the unit conversion. Make sure that I have the correct scale. Click OK. And then I have my 2D drawing, and I can start to draw from this. I can see all of these layers actually here in my drawing layers window. And I can actually turn on and off the ones that I don't need. It is very important to work in a clean and a consistent AutoCAD drawing. So if you have some lines which you are importing, you have to make sure that it is consistent and it is as helpful as possible. Maybe that is also a task that is done in the drawing itself before importing it to AutoCAD. So I can just actually start placing my columns on these points. Or I want to start placing some walls. I can also choose line by selection. And I am automatically created, I'm already generated some walls. I can also work on 3D AutoCAD files. So I actually have one right here. Let's see, I just drag it here. Do I want to save? Again, I'm prompted with the layers that are created in the CAD file. Let's say I just want this one. Really, I think I just want that. Again, this is very important and a good rule of thumb, especially when dealing with complex drawings like this one, for example. It has a lot of lines that are created in the AutoCAD. Of course, this can be managed in FEM-Design. You can just delete the lines that you don't need. But a good rule of thumb is to have the drawing already optimized in the CAD drawing. So get rid of any lines that you don't want to use and just make use of the of as little lines as possible so you don't get confused. Actually have this model here. This is the actual structural model from that drawing. It's been modeled with shells, and I can apply loads. can apply, and I can apply loads and then perform a structural analysis. For this particular example, this is a steel staircase, and I was looking at the von Mises stresses in the shells. These are the results that were interesting for me. Okay. Let's keep going. I'll just go back to my model here. And we've talked about, of course, there are several other elements, which I'm not going to go into detail here, like modeling tools like fictitious bar, fictitious shell, line point connection. These come useful when specific cases, which we will not go into detail right now. I was mentioning the IFC connection, which is very powerful and has been very, very thoroughly developed in the latest version. I would actually encourage you to go to our web page and see our past webinars at strusoft.com. The IFC feature is described and presented in detail in this webinar, happened about 2 weeks ago. So please go here and check it out if you're curious to see how IFC works. Some very nice models presented by my colleague Akos. Again, there's so many elements that I want to show you, and I'm just hoping we can get through all of them. We have 1 hour available, so let's try to go through as many possible that I have planned. If we take a look at the loads tab, we can actually see a wide variety of loads that I can apply to my structure, starting from point loads up to surface loads, then temperature variation loads, line stress loads, mass and seismic loads, footfall analysis, some time history analysis input, like excitation force or ground acceleration, and some macros, which are actually, we're going to take a look at this, the wind macro. In this structure right here, I can actually, if I want to apply some wind loads, of course I can do it manually and apply it manually as line loads, maybe some point loads on my steel skeleton here. But the wind macro actually generates the wind load automatically for me. And to do that, I need to apply these covers. And these covers, if I just start drawing them like this, are actually some membranes which take the surface loads and distribute them to the supporting structure. I can see that once I draw them, some areas of distribution are automatically created. Just have to make sure I put them on the right points. And I can see how the loads, how the regions will distribute the force to the supporting structure, which are, in this case, my beams and my columns. So once I have these covers, this is specifically useful when having a large structure and I want to generate the wind load automatically for my whole model. And I go back to loads, and I was looking at the wind macro, and I'm looking at a generic building. Again, here is where the command prompt comes in useful. let's say I'm using this for the first time. I'm actually, if I check the command prompt, it says select vertical structural elements to specify external wall of the building. This is very helpful and tells me what I need to do when using this tool. So I actually select these covers, which will be used as external walls for the software to determine which is the exterior side. And I do that for all of my sides and for the roof. I hope I can manage to select it. Oh, I need to select the flat roof and then choose a direction. Let's say this one. Okay. Once I've done that, I'm ready to generate wind load. Here are the parameters that I set, wind speed and the terrain type. Click OK. And load cases are generated automatically for my structure. I can check them here. I have some of them in all directions and different scenarios and load cases. I can see that these are created automatically for me. I can use them or I can choose to delete some of them if I don't consider necessary. And I can use them and mix them in some load combinations. Again, this comes in very useful when I'm dealing with large structures and I don't want to spend any or a lot of time in assigning line loads to my frame structure or something. And again, there are all types of loads, as I said, as I mentioned before. We won't go into all of them. There wouldn't be enough time for it. But please let us know if you want to see any of these functions. Is it whether it be loads or structure elements or any types of analysis, which we'll take a look at in a second. You just contact us and we can get back to you and show you live in a quick demo. That's the best way to know how FEM-Design works. Okay, let's take a look at some of the calculation types. In FEM-Design, you have a large number of calculations that you can run and get the results for. A very interesting one, and this is the newest one, which came out in FEM-Design 20, is the bedding modulus calculation, which actually allows you to calculate the bending modulus for a foundation based on the soil properties automatically. You define the soil and the bedding modulus is calculated automatically from that. We actually have some presentation about that in one of our previous webinars. So we won't go into detail right now, but just so I mention it. You can perform an imperfections calculation, load combinations, and here again, we have different types of calculations like nonlinear behavior of structural elements, plastic behavior of structural elements. You can actually set plastic limits for your supports or elements. If you have a look here at the degrees of freedom and the stiffness and all degrees of freedom, you can set a plastic limit in the respective units. and anything above this plastic limit will be distributed to the other supports in this case. So you can perform an analysis like that. Eigenfrequency calculation, stability analysis, seismic analysis, footfall analysis, time history analysis. I planned to have a look at some of these. So if I actually I have a steel element, I have a steel structure right here. So I can very easily, let me just hide this cover. For now, I don't need it. So a very useful tool is the shell model for steel elements. If I have a steel beam, I can actually convert it to a shell element automatically. Then I can perform a local analysis, for example, on this one, study for local buckling on a shell model of that beam. And dealing with shells, I have several other options. I have all the tools for a shell. So I can actually create holes in my shell, in my beam, like this, of course, any shape. And I can run a separate analysis for this type of element and study its local behavior, for example. And then I can actually just switch back to bar model when I'm done, like that. I have an element which I've run a calculation for, just so we see some of the options that it has. I have a beam here, which I've modeled as a shell. See, I've made some holes in it. And you can choose to see the Eurocode verifications for it. You can see here the verifications for flexural buckling and lateral torsional buckling with the deformed shape here. And the Eurocode sections from which these verifications and calculations come from. Then at the end, I actually get a summary of all these utilizations from stresses, flexural buckling in the weak direction, lateral torsional buckling, local buckling in this specific case. This is just a quick example of how you can use it. Since we're talking about steel, I actually have a example here, and I thought I'd mention a second order analysis for elements. You can perform that in FEM-Design. You can consider the imperfection calculations according to the Eurocode formula. And this chapter right here, 532, it says here, as an alternative, the shape of the elastic critical buckling mode of the structure may be applied as a unique global and local imperfection. The amplitude of this imperfection may be determined from this formula, and this formula is used in FEM-Design. So I will calculate the imperfections and choose my desired shapes like this. And from those, having that calculation, I can, as I saw here, I can choose a type of calculation, which is second order analysis. Tick that box and then choose the imperfection shapes, one of the imperfection shapes that I want to look at from my previous analysis, which is basically a stability analysis with the imperfections. So we'll do that second order analysis based on those, taking into account those imperfections. Of course, this was a quick demo suitable for this type of intro webinar. If you want to learn more, of course, you actually have a whole theory of that in the manuals or in our wiki, FEM-Design wiki, which is available for you online. It's very well structured and you can see the new features, the manuals, truly a wiki page for the software. Of course, there are several types of analysis that we won't go too much into detail right now. We mentioned the design modules. So let's have a look at some of the design modules. Again, as you can see here, there are several design modules, starting from foundation design, concrete design, steel, timber, masonry, and composite. I think we can start and have a quick overview of some of these design modules, just so we can take into so we can fit everything into our allotted time, allocated time. So I have some models prepared here. The reinforced concrete design, again with its own subdivisions for bar reinforcement, surface, punching reinforcement, concealed bar reinforcement. Oh, this is from design 19 actually. If I have a look here, one of the 20 models. This I can actually design for fire as well, for the bars. Okay, but I have an example ready-made for a concrete shell, concrete slab here. I have made a design, and I can see the utilization for bottom XY direction and top XY direction for my reinforcement. I can perform an automatic design where I set my parameters, a base net, which in this case is applied with a diameter 10 and spacing of 150 all across my slab. The area of reinforcement, which will be generated from this parameters, and the additional reinforcement, which will come on top of that in the regions where it is necessary. A good representation, graphical representation of this. If we take a look at this span here, I can see I have a diameter of 10, with a spacing of 150, which spans from this side to this side. And then a different additional reinforcement area, which is actually 8 by 150. And again, I can choose what kind of parameters I can use to determine that, to allow the program to insert into my design. So I can choose any of these diameters or remove them. Of course, I have the manual design tool as well, where I can just draw by hand any areas of reinforcement that I want in specific areas. I mentioned the punching reinforcement. Where you can check the punching areas, or you can also design them. And you have different types of punching reinforcement layout: stud rail, paygo products, bended bar, stirrup. And you can set up the parameters. The results for this shell, for this concrete surface reinforcement and punching reinforcement, is also very helpful in determining what kind of reinforcement you need. You have all sorts of results here. You have required reinforcement, which gives you an idea of what, of course I need to be here, which gives you an idea of the amount of reinforcement that you need. You have the applied reinforcement, or the missing reinforcement, which is very actually important, where you can see where you're missing any reinforcement and how much. These are values which you can set. The maximum value is automatically here. And of course, you can find also local maximum and minimum. You can see a detailed result of these calculations. If you right-click, if you select the detailed result tool, and then you click on any point of the shell of the plate, it gives you a detailed calculation of this section, which with the properties, applied reinforcement, the forces that have been used, internal forces, and then design forces. The sections with a graphical representation of the tension and compression forces in the concrete section. Of course, interaction curves based on applied reinforcement, the utilization. All available in this documentation section. I've just looked at this plate, horizontal plate, but that is also available for concrete walls. You can define and design the reinforcement for the walls as well. Actually do buckling lengths and set the lengths for that. Let's have a look at the steel design module as well. And for this, I will use this model. So looking at the steel design module now, I can see that I have, again, different sections for steel bars, steel bar shell model, which we actually saw already, steel joint, in steel bar fire design. In this particular model, I have already defined some steel joints, which I wanted to look at. And I think it is it's a feature that I like, and I thought I could show it to you. It's the steel joint module, which is actually also a standalone module and an integrated feature. So you can use it on the 3D model directly. I'm looking at the steel joint utilization right now. And I have all of these circles are joints that I have created and verified. Of course, this is the color scale for utilization. And if I can choose these joints and see the joints in a 3D view here. I have them. This is the steel joint module. And I can enter all of these components here. I can customize them, change their dimensions, their materials. This is the thickness. For end plate stiffeners, diagonal stiffeners, if it's the case, the haunch and the bolts and the welds. And I get a detailed calculation here for these components, including the stiffness calculation, the rotational stiffness of the joint. According to Eurocode, I can see here the stiffness. Once I'm done editing my components, I can click Finish, and this stiffness is calculated, and I can choose to apply it on my connecting components here and run the analysis with the correct stiffness. So it will calculate the stiffness for that respective joint, apply it and use it on the 3D model. So I can actually see the behavior of the structure with the correct stiffness, with the rotational stiffness calculated according to Eurocode. There's also other components of the steel design module, like the steel bar fire design, which is very interesting, and I encourage you to explore it and see how it works. And of course, we're here to help you and guide you through that. Real quick, I want to move to the timber design module, which is a very interesting module, especially with the CLT component. I have here a model which has some CLT panels defined. The calculation is already run, so I have some results. I can see here the results from a very advanced CLT module. I can see the laminated shell stresses, so I get all of these shell stresses for my panels, some shear forces, stresses, sorry, as well. And I can actually see those stresses on my shell. And I can see it for my individual layers as well. For the CLT. The CLT You can customize your panels and create your own panels, and of course choose from a library of existing panels from some of the manufacturers. If I go to structure and maybe have a look at it real quick. Here I can see some cross-laminated boards, and I can choose to have it as an orthotropic shell or a cross-laminated timber. So here is some already predefined libraries of elements, and I can see all the layers with their respective properties, and I also can create my own. It's very, very detailed and advanced calculation module, very powerful calculation and design module for CLT. You can set the buckling for the vertical walls, and you can set the buckling in any direction for the walls. I encourage you to actually visit our website and read about a very nice project in Australia, Sydney, Australia, which was designed using FEM-Design. It is a 100-meter tall hybrid tower, will be the highest commercial hybrid timber building in the world. We have had a webinar as well, specifically for this project, in collaboration with Eckersley O'Callaghan in the UK, in London, UK. And they have talked about the project and how they used FEM-Design to calculate and design the CLT panels and the timber frames. And they explain how they divided this the structure into they're called habitats like this, and how they use it to calculate the loads and the stresses and the design verifications for the CLT. Some irregular shapes as well they had here, some curved shapes. It's a really interesting presentation of the project, and it shows you how you can use the CLT module, how it has been used on a real project. And the recording of the webinar is also here, and you can rewatch it whenever you want. If you are not using FEM-Design yet, it is very easy to apply for a trial and get started with testing and using FEM-Design. Just go to the Get Started button on our website and fill out the form for a trial license here and submit. Again, I'll just post our contact information here. Just contact us directly if you have any questions or you need any help with FEM-Design.